this morning, we've been looking at linear functions. We're going to move to our quadratic functions and to be doing some more specific thinking about the nature of quadratic functions and some information that we can glean from the equation of a function or from the drawing of a function. So, I just want to start with asking the question, what is the maximum value of a linear function? What is the maximum value of a linear function? Infinite. And generally that is the answer. If we've got an unbounded linear function, when we talked about our domain and our range, unless we're actually specifically limiting it, they will be infinite, won't they? We talked about that with our notation, negative infinity, infinity, and negative infinity to infinity in the range. So unless we actually specifically bound it, they're infinite, aren't they? That is not the case with quadratic functions. Quadratic functions will have, again, unless we bound them specifically, but a general quadratic function will have either a maximum value or a minimum value. Either a maximum value or a minimum value. If I draw what we kind of regard as the kind of the normal shape of a quadratic, which means opening up to the top, like that, we can see that quadratic function has a minimum value. It does not get any lower than that. That is its minimum value. If I draw it the other way, what we might describe as upside down, that there is the maximum value of that function. Now the first one there, this one has no maximum value. It goes off to infinity, but it does have a minimum value. This one here doesn't have a minimum value, but it does have a maximum value. Okay? So we're going to ask the question, how can we calculate that? Given a quadratic function, how can we work out what that maximum value is or the minimum value is? Okay? So we're going to run through a few steps to do with that. First thing, let's recognise the fact that quadratic functions are symmetrical. So let's draw a nice, easy one to start with. Let's say y equals x squared plus 1. Okay? Y equals x squared plus 1. Looks like this. I haven't drawn that very well. It should cross there at 1. And we can look at that, and we can probably just work out straight away that its minimum value is 1. But it's good to use that shape to start with, because we can see with the y-axis down the middle of it, we can see that it's a symmetrical function. It is exactly the same on this side of the y-axis as on this side of the y-axis. We see that? Yep. Now if we move our quadratic function anywhere we want to on the number plane, it still remains symmetrical, left and right. It won't necessarily have an axis down the middle, but it will remain symmetrical. So if we draw a quadratic function that looks like this, okay? A quadratic function that looks like this crosses the x-axis at -2 and at 0. As an interesting axis to consider, can we calculate its equation from that information?
Yes.
We can. How do we do it?
Plug in the numbers into the...
Well, we can do some of that, but that won't necessarily give us the equation, will it? Because well, we know that this point here is 0, 0, and that point there is -2 and 0. Well, that works for linear functions, doesn't it? Yeah, it doesn't work for a quadratic. But what else do I know about that? What do we call these things where it crosses the x-axis?
Intercepts.
Intercepts. Other words, we we call, from quadratics in particular, or for polynomials generally, we call them roots of an equation, where they cross the x-axis. It also tells us where the function equals 0. Okay? So both of those are roots of the equation. It also helps us to work out, using brackets in our null theory, what the equation will look like. Because at both of those places, the function equals 0. And so, when we have x minus 0 and x minus negative 2 in those brackets, one of those things will always equal 0 at one of those two places. We're kind of working backwards from where we were when we had a function, and then we factorised it, and we go, well, where does that equal 0? One of those brackets equals 0. We're now working backwards from that. We know where it equals 0. Can we come up with the brackets from that information? Does that make sense? So we can put into any function x minus one of the roots, x minus the other one of the roots, and come up with its equation. Let's continue on with this one. I'll just write that off so we can continue on. Let's continue on with this one. What's x minus 0? X. What's x minus negative 2? X plus 2 equals 0. And if we expand that, x squared plus 2x equals 0. Okay? And so one of those two things equals 0. And if we now just make that as the general form of the equation, so the function equals that. Okay? So using the roots, we can come up with the equation of the quadratic. This is a quadratic thing, absolutely. Doesn't work for all functions, but it certainly does work for quadratics. So x minus, let's just call one root a, x minus b, and we expand and we get a function. That's a really good thing to remember. Okay, that's a little tangent. Let's ignore that little tangent for now. Okay, because I want to go back to the information we had before. This is symmetrical. Quadratic functions are symmetrical. So that means if I were to draw a line down the middle here, it's the same on both sides. And if I draw a line down the middle, it's going to cut the point where it is at its minimum value. Okay? Where it's at its minimum value. If it's symmetrical, can I work out what the x coordinate is, or the x value is, where that red line is?
Yeah.
Yeah, it's at -1, isn't it? Halfway between -2 and 0. So, its minimum point, its minimum value is when x equals -1. Just using the symmetry of the quadratic shape, the parabola shape. If there's a root at -2, a root at 0, then I know halfway between those roots is where it's either its minimum or maximum value, depending if it's normal or upside down. Okay, that doesn't tell me though what the value is, does it? It don't tell you that's where it is. But now, using my function equation, I can say, well, if x equals -1, what is the function at -1? We did this a couple of weeks ago, maybe even last week. What does that mean? I can put -1 wherever x is. Okay. -1 squared plus 2 times -1 equals 1 minus 2 equals -1. So the value of the function there is -1. Not only is it at x equals -1, but it's also at y equals -1 there as well. So its minimum point is -1, comma, -1. -1, -1. Okay? So I can use the symmetry properties of a function to work out its minimum or maximum point. The other term we use for that as well, I forgot to mention this before, is we call it a turning point. Because it's where the quadratic kind of turns around. It's going down, it's got a negative gradient, all the way to that point, then it turns and heads back in a positive gradient, heads up. It's turning point. That's a general term that we will use going forward in advanced mathematics. A point where a function either changes from negative to positive gradient or the other way around. Okay. So that's really helpful when it's drawn for us or when the equation is already in a form that tells us its roots. So if we've got a function of x equals x minus 1 brackets x plus 3, x minus 1 brackets x plus 3, where is its minimum? Okay, this is going to be a positive shaped parabola, positive x squared, so it's going to be a normal shape, it's going to have a minimum value. Where is its minimum? Well, it's halfway between its roots. Where are its roots? It's actually not minus 1 and 3. It's at 1 and minus 3. So remember, it's the negative of that number there. Okay? Right, so the roots for this crosses the x-axis at x equals positive 1 and negative 3. Okay? So where is its minimum point? Halfway between these two. So the minimum value, or the turning point, is at x equals negative 1. Let's pop that in to our equation. Let's see what we get. So function of negative 1, what do I write? Negative 1 minus 1 plus 3. Okay, so what's negative 1 take away 1? Negative 2 times negative 1 plus 3, positive 2 equals negative 4. So its minimum, its minimum value is negative 4, and the turning point therefore, turning on, it's not a tuning point there. Turning point is negative 1, comma, negative 4. Okay? So using the symmetry properties, I can quickly work out where it's where the middle of the parabola is, and therefore what its minimum or maximum value is going to be. Any questions about that? I'm going to do one, I guess, with just a little bit of a different shape. Okay, couple of things to notice about this. I've put in two differences into this one now. What have we got? We've got, first of all, a negative out the front. What does that mean? Yeah, it's going to be like an upside down parabola. It's going to open out to the bottom. We're going to have a maximum value, not a minimum one. That's great. What else? What's the other difference? Yeah, so there's a 2 in front of the x there. It actually means we've got to be a bit more careful about what our roots are going to be. Okay, so and my root of my first one is going to be, sorry, x equals negative 7. Okay, we can see that one, that's okay. The other one though, it's not at x equals 3 because there's a 2x there. So we have to be a little bit more careful now. So we're saying x equals negative 7 is one of the roots, but the other root is when this whole bracket equals 0. So when 2x minus 3 equals 0, so when 2x equals positive 3 and x equals 3 over 2. Okay, so just got to be careful with finding that root there if there's a coefficient of the x that's not 1. Okay, just got to be careful with that. But there are my two roots, negative 7 and 1.5, 3 over 2. but we go through the same steps. So now I say, so the maximum in this case, because it's an upside down one, the maximum is at, how do I find out where the midpoint of those two is? What's a quick way to find midpoint? We haven't been doing it because it's been kind of obvious and we haven't actually need to think mathematically about it. But what do we do when we find midpoint? Yeah. Sorry? Yeah, so what, how do we do that mathematically?
Plus them together and divide by 2.
Perfect. All right. -7 plus 3/2, all divided by 2. And we can do that in our heads, or you can use a calculator if you want to. -7 plus 1.5 is -5.5, or as an improper fraction, -11/2, all divided by 2. Therefore, that is -11/4. Okay, and so our maximum value is at -11/4. So now we say, what is the function value at -11/4? Put it in. -11/4 plus 7 times 2 -11/4 minus 3. Okay, a little bit of fraction arithmetic here. We've got, that becomes,
Where'd you get the 4 from?
where? Here.
Yeah.
So I'll do an extra step here. So it's that's a negative, what did I say that was, -11/2 over 2. So that's what that becomes. And when you've got a fraction over a number, you multiply the denominator by this denominator. So just multiply those 2 and 2. So what's -4 plus 7? Well, that's 28/4. So it's 17/4, negative. So I'm just going to write this like this just so we can really see where it comes from. -17/4. And then this is -22/4 minus 3. So it's -12/4. So it's -34/4. Got that right? I hope so. Negative is going to come up with a positive answer. 17 times 34. Oh, that's nasty. 289 times 2. 578. Do it. 578. 4 times 4 is 16. I can simplify that. Divide top and bottom by 2. 298 over, so 289. 289 over. Not a nice number. That's all right though. We're happy with that. So we've, let's turn that into a mixed number. How many 8s go into that? 35, 36? 36 and 1/8. So that's the same as 36 and 1/8. So our maximum point is, that's the x value, that's the y value, so the maximum, so I'm just coming up here now, the max is -11/4, comma, 36 and 1/8.
Is that the turning point?
Oh, yeah, that's the turning point, yep. I'll change that to -2 and 3, please. Okay? Yeah, it's the turning point, but in this case it's a maximum turning point, because it's an upside down shape. That's right.